Welcome back. So next I want to talk about how we can represent aliases with so-called access paths. So let's take a look what that term actually means. I may have accidentally used it a couple of times already. So an access path, it has the following form. So it's basically, you could say, a sequence of field access expressions. So you have always at the very beginning a local variable, which I here call v. Okay, so this is really just a regular local variable. So you could say it gives you a memory location on the stack, right? That's basically what the local variable represents. And then, yeah, you can then dereference this to these field accesses that you see here, right? So f and g and h, they are field access expressions. So in Java, for instance, that would now, if v is actually pointing to an object, that would dereference the pointer, resolve its object on the heap, and then access its field f from that. And that may point to another object. And again, by using this point operator, you're dereferencing that pointer and then accessing field g of it, and so on, right? You can use these access paths of the structure, right? So local variable with one or more field accesses to actually refer to objects. And in pointer analysis, or also in particular in alias analysis, it makes a lot of sense to use them as representatives for objects or as object descriptors, like I want to show you here. So for instance, let's take a look at this program. Here you see, this object is being assigned to X and then to different kinds of field accesses like you see here. Then you can use these access paths here to refer to this particular object that is being allocated here, right? So this set, for instance, could say, I'm now referring to the object that is being pointed to by X and only by X. Okay, so by that particular variable here. And then looking at the program, you would know that, okay, he's talking about this particular object being allocated here, okay? Similarly, here this set would tell us we are now talking about the object being pointed to by X and by a.f, which is still the same object, right? Although the set here changed and the set of access paths referring to that object now changed. And these two are now aliases, right? Because we know they are pointing to the same object, and it's the object described by the set, okay? So we know they are aliased. Similarly now here, this set is being extended to b.g, okay? And now something interesting happens. So let's take a look at the next statement here. So we are assigning b to c.h, okay? And b occurs in here, but this is basically saying c.h is basically the same as b after this assignment, right? So, and we previously had b.g in this set. So this means c.h.g should now also be part of the set, right? Because b and c.h, it's really the same, right? And that's basically what we get after this assignment here. So we still have the same set that we originally had here, but we now also have this additional alias here, right? c.h.g that is also pointing to the same objects, right? And this is simply because we already had this alias relationship before, this is now being added to the set. In addition, we are now having a different set, which is talking about a different object, right? So here we are talking, so in this right-hand side set, we are talking about the object that is being allocated here. Here we're talking about a different object. It's actually an unnamed object. We don't know whatever has been assigned to B, right? So we don't know where B has been allocated. It's not part of this program that I'm showing you here. But nonetheless, through the set, we can say that c.h is actually aliased with that object, right? Or it's aliased with B, and both are pointing to that same object. That comes back to what I talked about earlier when I was talking about alias analysis versus points to analysis. So although we don't even know this allocation side here, we can still say through these access paths that we don't care about the allocation side, but both of these access paths are actually pointing to the same object, no matter where it was allocated. Okay. So what's now very interesting, I find, about this set-based representation where you have these sets of access paths is that you can encode both may and must alias information with these sets of access paths at the same time. And I want to illustrate that using this example here. So here we have in this block 3 different variables being assigned newly created objects. Okay, so at this point here, these variables are all not aliased. Okay. Then after this statement here, y and x may be aliased, and after this statement here, z and x are definitely aliased. Okay. But because in the beginning there is no aliasing, we would start with alias information that looks like this. So we have one variable x that points to an object that nothing else points to, so it's a singleton set. And the same holds for y and for z. Okay. This also still holds here before the assignment. But now after the assignment, x and y actually become part of the same set, right? So note, this is a strong update here. Okay, so we are discarding this set here. It's not present anymore. But at the same time, we're merging these two to form this new set. And we can do that because, well, definitely we know for sure here that y has been assigned the same object as x, right? No matter what, there's nothing that could change that, and therefore this is also being represented by the set. So here the set now says, I'm now talking about 2 objects. One is being pointed to by x and by y, and the other one is still only being pointed to by z. Okay. If I look on the left-hand side branch here, it's different. So in particular here, I'm retaining the set that I'm getting from above, right? Because that's basically just simply falling through this branch here. But at the same time, assuming I've already merged analysis information from the right-hand side branch here, I get this set here from the right-hand side also merged into here, right? So this is why this appears here. This is basically the merged result that I get just before the statement. And what is this now telling me? That's interesting, right? So by basically looking at the sets, you can already see that there was some conditional branch going on because the result regarding x is now inconclusive, right? So x could be pointing to an object that only itself points to, but it could also point to an object that also y points to, right? And similarly for y itself, it's basically the same situation. So that means in this case, well, what does this tell us, right? So which variables are alias doing? I'll still be getting back to that. Bear with me for another minute. What's interesting now is that when you assign the statement here or process this assignment statement again, so x is being assigned to z, then we now know for sure that z is pointing, well, we know for sure it's pointing to whatever x was pointing to earlier, right? But looking at this result here, we don't know exactly what x was pointing to earlier. It might have been pointing to this guy and might have been pointing to that guy. And that's why these two sets are being extended here, right? So this set is being extended to that set because z might now also point to this. And this set is being extended to that set. And the previous set here, that is being strongly updated away, so to say, right? So z is definitely not pointing to what it was pointing to earlier. So that set's being discarded. Okay. So what's important now is that if you look at such a situation here, okay, where x is part of this set, but also of the other, it means the following. So it means there is an object for which it may hold that only X points to it. That's this one, okay? But it also means there's another object, or possibly the same, for which X and Y may point to it, okay? Like you see here. And the thing is that every such set represents a unique possible runtime object, okay? And this actually allows us to do some very powerful updates, because out of this you get some strong invariants. And if you are interested in reading up the maths, there's this paper here by some esteemed colleagues of mine that explains this in a bit more deeper fashion. And also there's more related work on this that's being cited here. But let me bring this across. So if at some statement S, it is possible for some concrete object to be pointed to by the set of variable vars, right? So we have some such set that I showed you. Then the set vars must be part of the abstraction at S, right? So you're guaranteed that this set and the complete set will be part of the abstraction, okay? And conversely then, the presence of vars in the abstraction indicates that there may exist 0 or more concrete objects which are pointed to by the variables in vars and no others, okay? So it's still an approximation. There might be 0 such objects, and there might be more such objects, but still you get this guarantee at least. Now, why is this interesting? Because both may alias and must alias information can be encoded this way. Let me show you how this works. So let's assume we want to determine may alias X and Y. And then that is the case if there is a set containing both X and Y, right? Because we have this guarantee that I mentioned earlier that if these two variables are alias, then such a set must be part of the abstract representation. We know that this definitely holds. That's the easy case. Now, we can also determine must aliasing, and that holds if there are sets that contain X and Y. Okay. I mean, that's clear. Otherwise, they wouldn't alias at all, right? So there are some sets that contain X and Y, at least one of them. And each such set that contains X also contains Y and vice versa. Okay. And that is interesting. So there might be multiple such sets, okay, because we aren't quite sure about the control flow, for instance, right? But if we have this guarantee that everything that contains X nonetheless also contains Y and the other way around, then we can still determine must aliasing. So let's take a look at this example here, okay? So let's say we have these two sets computed at some statement. Then does it hold that X and Y may alias? Well, it definitely holds, right? Because there is a set that contains both X and Y, okay? Is it true that X and Z must alias? Well, there is a set that contains X and Z both, and there are actually two of them, and all of them, you know, all sets that contain X, they also contain Z and the other way around, right? So this is true. Must alias X and Y? Not so much, right? Because there is a set, this one here, that does contain X and not Y. So it means there is a program execution that might have led us to the statement where Y is being assigned something else, right? So it's not being assigned or no longer being assigned the object that X and in this case also Z point to. So this would be false. Okay. Now you might think, okay, that's a nice representation, right? So you can, using the same representation, just a set of access paths represent both a may and a must alias analysis. Okay, fair enough. But actually this is even stronger. So this representation allows for strong updates, also on pointers that involve may aliasing. And that's something I want to explain on the next slide. So this is probably the most complex slide for this week. So bear with me. I'll try to go through this slowly so that everybody can follow. Let me get back to this example that I showed you, right? So we already talked about how these different alias sets are being computed here, okay? But now let's look into strong updates here, okay? And in particular, let's take a look at this particular situation here, where we only know that y and x may alias, right? So let's double check that, right? So they definitely may alias because there is a set that contains both of them, right? And this is because of this branch, right? Because you can go along here. There can be the situation that these two variables alias, but they don't have to alias, right? And you can see that because there is a set that contains y but not x, and actually even the other way around, right? And this is because you can also go along this control flow path along which the two don't alias, okay? Now let's assume the following. We are doing, again, the same client analysis that we had earlier, a field-sensitive constant propagation where everything is initialized to 0. And now let's take a look at what we could compute in this case. Okay, so here I'm using these couple of statements here. And this I just basically added here to do something interesting in terms of constant propagation. But here we still have the very same situation that you found earlier on the slide, right? So x and y may be aliased, but they don't have to be. And now we can take a look at what's being computed here. Okay, so like I showed you already on the previous slide, when you have this assignment here, this is being updated like this, right? So Z is being updated to this set and also to this set, and the old singleton set for Z, it disappears. So we already saw that. It gives you this analysis state, okay? And how does this now impact the client analysis, in this case, the constant propagation? Well, basically, you would update each of these objects represented by these sets one by one, right? So initially, like I said, we have these objects here, and they're initialized to 0. Actually, the one for Z we don't care about, so I didn't write it down here. But this is our initial analysis representation. And now after this update here, we get this one, right? So simply the set that we had for X, it's being translated into this set here. And the set that we had here, it's being translated into this set. And the remaining analysis information, in particular, the mapping to values that was not updated, right? Because there are no numeric values being updated here. Okay, that gives us this analysis state at this program point. Okay, fair enough. And now we are doing this update here. Okay, so we are updating x.f. Okay, and just to double check, also here we are still having the situation that y and x, they do not alias, right? They may not alias. So they alias in this case, but not in this case here, right? So we still have may aliasing relationship between x and y, but no must aliasing relationship. But nonetheless, I can actually do a strong update here. That's peculiar, you may think. So why is that? Well, we can still look at these object representatives here in isolation, right? So we have an object here that x definitely points to, right? So it's looking only at this object, right? And not at the others. We definitely know that x points to this object here, right? And the representation here that I have here, it represents that very object, right? So therefore, it's safe to update this number 0 here to 3, like you see here. Okay. This obviously doesn't get updated because there's no x whatsoever, right? So this just remains what it was before. Interestingly now, this object here as well, well, it's also being pointed to by other variables, right? So it's not only being pointed to by x, but also by y even and by z. But this we can also update, right? Because looking only at this object in isolation, we know for sure that this is an object that x points to, and therefore we can strongly update its value, like you see here. Okay. And that's actually quite nice, right? So you have strong updates, not just on this particular, well, in the particular case where you have must alias analysis relationships, right? But also in cases where you only have may alias relationships, because in this case, actually, the aliasing between these different variables, it doesn't matter so much. It's sort of like we have re-indexed the data structure, right? So here we are indexing on individual objects, and they're just being represented by the aliases that point to these objects. But each of these objects or the static representatives, we can update individually, right? And then the set of variables that point to these objects, well, they still matter, right? Because we use them as as names basically for these objects. But the aliasing relationship between any two of these objects or variables that point to these objects, that doesn't matter that much anymore. Now, if you got confused by these kinds of sets here, I have a bit more object graph-like representation that I want to show you that might make things clearer. So let's take a look at this. So here, this set, or the set of mappings, I should say, represents exactly this data structure in memory. So you have an object, this one, that x and z point to, okay? And that has a field f that points to some memory location that stores the value 0, okay? Then we have this variable y, and y may, and that's this case, point to a distinct object that then also has a field f that points to 0. I didn't draw that here, but basically you would have to have another f field here, okay? Or y can also point to the same original object that we had up here, okay? That's this case. Okay, so about y we don't really know. That's this may aliasing relationship that we had earlier. And now remember, we saw an assignment of x dot f to the value 3. Okay, and by looking at x dot f, I definitely know we are talking about this memory location. Okay, and so I definitely know this memory location needs updating to 3. So let's just do this. Okay, and then that's how you can explain how we arrive at this representation now. Now we still have an object that x and z point to, and looking at its field x as f, we get the value 3 now. And y still might point to the same original object down here, which has field value 0, which I didn't draw. But it might also point to this object here whose field was updated. Okay, and that's the representation that we have down here. Okay, so what's important is that in this notation, these two objects, basically this one and this one, they are being kept separate, okay? Although y may point to them, right? But because they're being kept separate, we can safely distinguish their values. So to recap, using these sets of access paths, Um, it's very powerful, right? Because using that, one can represent both must alias and may alias information. Every set represents a unique runtime object through the variables pointing to it. Um, Something that I didn't explain today, but which might be interested for those of you who want to do some further reading. There is some special handling required for pointers that are loaded within loops, because when you have that situation, well, the statement loading a pointer within a loop, it might load different pointers or different objects in every single loop iteration. And so if you are just talking about a pointer or an object at a given statement, like you do in a must alias analysis, but that statement is within a loop, then you might still have the situation that you might actually be talking about multiple objects, because depending on the exact loop iteration, you might be talking about a different one. And there's a so-called focus operation that deals with this, and that lets you reestablish a certain level of precision by basically, again, splitting your abstract representation. So you're basically splitting apart the object of the current loop iteration from the object in all the other loop iterations. And that is often helpful enough to keep a certain level of precision in your analysis. Getting back to the representation that we had here, the set-based representation, it allows for strong updates as different potential objects are kept separate in the abstraction, right? And so we saw that these strong updates even operate in cases where you have a may-alias relationship, and that's really neat. Now, in the final video that will follow, I want to talk about why precise pointer analysis is not a distributive problem, and why that matters for everything else that is coming later. I will talk to you then.